We live on a sphere of rock and metal wrapped in ocean and air, turning steadily through darkness and light, as it has for over 4 billion years. The ground beneath us feels utterly still, solid and dependable, anchoring everything we know to one seemingly motionless place in space. Yet right now, at this very moment, the surface we stand on moves through space at extraordinary speed, carrying every mountain and ocean along with it. This motion happens in perfect silence, with such smoothness that no instrument could detect the slightest vibration, and our bodies register nothing at all. The night sky stretches overhead, scattered with points of light that seem fixed and eternal, marking familiar patterns our ancestors knew by different names centuries ago. We look up from our particular place on the surface, perhaps from a bedroom window or a quiet yard, seeing the stars as distant and motionless against the dark. Yet both stillness and motion fill this moment together. The ground beneath us and the stars above us, all participating in journeys that span distances our minds struggle to fully grasp. We stand at the center of our own experience, feeling perfectly at rest, while the universe moves around us and carries us forward through space in ways that become remarkable once we pause to follow them. You are listening to the Drowsy Astronaut, where we explore the cosmos slowly and thoroughly, taking our time with the details that make the universe quietly remarkable. Tonight, we follow the nested layers of motion we all experience every moment, beginning with the spin of Earth itself and expanding outward to movements so vast they include entire groups of galaxies. If you are settling in for the night, wherever you happen to be, you might leave a comment about where in the world you are listening from, what time it is there, whether darkness or daylight surrounds you right now. If this journey through cosmic motion brings you some calm or curiosity, the like button and subscribe option are there. Just an invitation to return whenever you need something gentle and real to think about as sleep approaches. The motion begins with rotation, the daily turning that creates sunrise and sunset, that sweeps the stars across the sky from east to west throughout each night. Earth completes one full rotation every 23 hours and 56 minutes, a period we round to 24 hours for practical timekeeping, though the actual sidereal day runs slightly shorter. At the equator, where Earth's diameter reaches its maximum at nearly 8,000 miles, the surface speed reaches about 1,040 miles per hour. That speed equals roughly 465 meters every single second, a velocity that would cross several city blocks in the time it takes to read this sentence. The speed decreases as you move toward either pole, following a simple geometric relationship tied to the circumference at each latitude. Someone standing at 45 degrees north latitude, roughly the position of cities like Portland or Montreal, moves eastward at about 730 miles per hour. At 60 degrees north, the latitude of Anchorage or Oslo, the rotational speed drops to about 520 miles per hour. Near the poles themselves, within a few degrees of 90 north or south, the rotational speed becomes almost negligible, just a slow pivoting in place as the axis turns. Standing at the geographic North Pole, the motion would feel different in character, though not in sensation, since all these speeds remain imperceptible to human senses. The pole experiences no eastward or westward movement at all, only a slow rotation in place, one complete turn per day, while staying at essentially the same point. The sun would circle the horizon during the 6-month polar day, neither rising nor setting, but spiraling slowly across the sky at a constant height. The stars would do the same during the polar night, wheeling around a point directly overhead, marking the axis around which the entire planet turns. This unique perspective reminds us that the rotation we all share takes different forms depending on where we stand on the spinning sphere. The reason we feel none of this motion lies in the nature of velocity itself, in the difference between speed and acceleration. Our bodies detect changes in motion, the push and pull of acceleration or deceleration, but constant velocity at any speed feels identical to perfect stillness. A passenger on a smoothly flying aircraft cannot feel the 500 miles per hour of cruising speed, only the bumps and turns that represent changes in that motion. Earth's rotation maintains such extraordinary constancy that it changes imperceptibly from one moment to the next, with no jolts or variations to alert our senses that movement occurs. The atmosphere rotates along with the solid surface, so no wind arises from the motion itself. Nothing pushes against us to signal the tremendous speed we share. This smoothness results from the immense mass and momentum of a rotating planet, a system so large that its motion continues with almost perfect uniformity. The radius from Earth's center to the equator spans about 6,378 kilometers, and rotating that much mass every 24 hours creates angular momentum that resists any sudden changes. Small perturbations occur over long timescales, slight wobbles, and variations that astronomers measure carefully, but from moment to moment, the rotation proceeds as steadily as any motion in nature. We are passengers on a platform that turns without variation, without pause, without any perceptible indication that it moves at all. Yet the motion leaves subtle traces, evidence that appears in patterns too large for us to sense directly, but visible when we observe the world carefully. The Coriolis effect emerges as one such trace, a consequence of rotation that influences anything moving freely across Earth's surface for extended distances. Air masses moving from the equator toward the poles deflect eastward in both hemispheres, not because any force pushes them sideways, but because they retain the eastward velocity they possessed at their starting latitude. As they move to regions where the ground beneath them rotates more slowly, their greater eastward speed carries them ahead of the surface, creating an apparent deflection to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection shapes the great wind patterns that circle the planet, the trade winds and westerlies that blow consistently in particular latitude bands throughout the year. High and low pressure systems rotate because of this effect, spinning counterclockwise around low pressure in the northern hemisphere and clockwise in the southern hemisphere, creating the spiral cloud patterns visible from space. Ocean currents follow similar paths, deflecting as they flow across thousands of miles of water, creating the great gyres that circulate clockwise in the North Atlantic and North Pacific, and counterclockwise in the South Atlantic and South Pacific. These patterns exist because the planet beneath them rotates, turning steadily eastward while the water and air move according to pressure and temperature differences. The Coriolis effect demonstrates itself in smaller ways too, though many popular examples turn out to be myths upon careful examination. Water draining from a bathtub does not reliably swirl one direction or another based on hemisphere, as the effect operates too weakly at such small scales and local disturbances dominate the flow. A precisely constructed experiment with a very still pool of water could show the effect over time, but everyday drains reveal nothing about Earth's rotation. Artillery shells fired across many miles do deflect measurably, and long-range ballistic calculations must account for Coriolis forces, or the projectiles will miss their targets by significant distances. The effect grows stronger with distance and time, becoming important only when motion covers substantial portions of Earth's surface. Day and night themselves stand as the most obvious consequence of rotation, the rhythm that has governed life on Earth since organisms first emerged billions of years ago. As the planet turns eastward, the sun appears to move westward across the sky, rising in the east as your location rotates into sunlight, and setting in the west as rotation carries you back into the planet's own shadow. The division between day and night, called the Terminator line, sweeps steadily westward across the surface at the speed of rotation, moving fastest at the equator and slowing toward the poles. Cities experience sunrise and sunset sequentially as the Terminator passes, with eastern locations entering daylight before western ones, creating the progression of time zones we use to organize our schedules. From space, the Terminator appears as a distinct boundary crossing continents and oceans, a line where the landscape transitions from the darkness of night into the colors of dawn, or from the light of afternoon into evening shadow. The boundary is not sharp but gradual, with twilight zones on either side, where the atmosphere scatters sunlight, even though the sun sits below the horizon. Astronauts aboard the International Space Station witness 16 sunrises and 16 sunsets every 24 hours, as their orbit carries them around the planet far faster than the surface rotates below. Each sunrise arrives after only about 45 minutes of darkness, the Terminator sweeping toward them at the combined speed of Earth's rotation and their own orbital velocity, creating a rhythm entirely different from the one we experience on the ground. The rotation itself has not always proceeded at the current rate, and it continues to slow gradually as the eons pass. Tidal forces exerted by the Moon create friction in Earth's oceans and solid body, friction that acts as a gentle brake on the rotation over millions of years. The same tidal forces cause the Moon to gradually recede from Earth, moving approximately 3.8 centimeters farther away each year. And the two processes connect through conservation of angular momentum. As Earth's rotation slows, the Moon must move outward to balance the books, maintaining the total angular momentum of the Earth-Moon system, even as it redistributes between rotational and orbital motion. This slowing accumulates over deep time into measurable differences that appear in the geological record and in careful astronomical observations. Each century, the length of an Earth day increases by roughly 1.7 milliseconds, an amount too small to notice in human lifetimes, but significant across millions of years. 450 million years ago, during the Ordovician period when the first plants colonized land and the seas teemed with trilobites, each day lasted only about 21.5 hours. The year contained roughly 410 days, because Earth completed more rotations during each orbit around the Sun. Ancient corals from that time preserve daily and yearly growth patterns in their skeletons, microscopic layers that record both the daily rhythm of sunlight and the annual cycle of seasons, allowing scientists to count the days per year in the distant past. Going further back, to the time when the Moon first formed about 4.5 billion years ago, Earth rotated far faster still, completing one turn in perhaps only 5 or 6 hours. The Moon hung much closer then, orbiting at a fraction of its current distance, and the tides it raised would have been enormously stronger, reshaping the young planet's surface with tremendous forces. Over the billions of years since, the gradual transfer of rotational energy to orbital energy has brought us to the current configuration, with 24-hour days and a Moon orbiting at a distance of roughly 239,000 miles. The process continues today as it has always continued, so slowly that countless human generations pass without any perceptible difference, yet inexorably working to reshape the Earth-Moon system over timeframes that dwarf all of human history. And this rotation, this daily turning at 1,000 miles per hour that we cannot feel, represents only the first layer of motion. The spinning Earth itself traces a much longer path through space. And that path represents another movement entirely, one that operates on a yearly cycle rather than a daily one, and adds far greater speed to the motion we already share. The planet beneath us spins, and the spinning planet moves, following an elliptical path through space that takes 1 full year to complete. Earth orbits the Sun at an average distance of about 93 million miles, a span astronomers call 1 astronomical unit, a measurement that serves as a fundamental yardstick for distances within our solar system. The planet travels this immense circuit at a speed of approximately 67,000 miles per hour, equal to about 30 kilometers every single second, where rotation, measured in the hundreds or low thousands of miles per hour, orbital motion reaches speeds more than 60 times faster, carrying the entire spinning Earth around its parent star. The orbit follows an ellipse rather than a perfect circle, though the deviation from circularity remains quite small by most standards. Eccentricity measures how elongated an orbit appears, with 0 representing a perfect circle and higher numbers indicating increasingly stretched shapes. Earth's orbital eccentricity stands at about 0.0167, meaning the orbit comes very close to circular, but not quite perfectly so. The difference between the closest and farthest points amounts to only about 3 million miles, a variation of roughly 3% compared to the average distance, small enough that the orbit appears nearly circular when drawn to scale. The closest point in the orbit, called perihelion, occurs in early January each year, currently around January 3rd or 4th, depending on the year. At perihelion, Earth sits about 91.4 million miles from the Sun, slightly closer than the average distance. The farthest point, called aphelion, arrives in early July, around July 4th or 5th, when Earth reaches approximately 94.5 million miles from the Sun. These dates seem backwards to many people at first, particularly those living in the Northern Hemisphere, where January brings winter cold and July brings summer heat. But the seasons have nothing to do with this slight variation in distance, and everything to do with a different aspect of Earth's orientation. From a vantage point high above the solar system's North Pole, looking down on the orbital plane from above, Earth's path would appear as a smooth ellipse traced counterclockwise around the Sun over the course of each year. The Sun itself does not sit precisely at the center of the ellipse, but at one focus, slightly offset from the middle, which creates the variation between perihelion and aphelion. The other planets trace their own ellipses in the same plane, or nearly so, each moving counterclockwise when viewed from above the North Pole, each following an orbit whose size and shape depends on its distance from the Sun and the particular gravitational configuration that determined its path billions of years ago. Earth's motion along this path obeys the same principles that govern all orbiting bodies, principles first fully described by Johannes Kepler in the early 1600s, based on careful observations of Mars. The planet moves faster when closer to the Sun and slower when farther away, sweeping out equal areas in equal times as it travels around the ellipse. At perihelion in January, Earth moves about 1 kilometer per second faster than at aphelion in July, a slight difference that helps compensate for the changing distance and maintains the mathematical harmony of the orbit. Gravity provides the force that holds Earth in its path, constantly pulling the planet toward the Sun, and the planet's sideways velocity prevents it from falling inward, creating instead the stable ellipse we trace year after year. This orbital motion creates our year, the cycle of seasons that governs agriculture, migration, reproduction, and countless other patterns in the living world. But the seasons themselves arise not from the changing distance between Earth and Sun, but from the tilt of Earth's rotational axis relative to the orbital plane. The axis tilts about 23.5 degrees from vertical, pointing in nearly the same direction throughout the year as Earth orbits around the Sun. During the northern summer, the North Pole tilts toward the Sun, bringing longer days and more direct sunlight to the northern hemisphere, while the southern hemisphere tilts away and experiences winter. 6 months later, Earth has moved halfway around its orbit, and the same axial tilt now points the North Pole away from the Sun, while the South Pole tilts toward it, reversing the seasons between hemispheres. The equinoxes mark the moments when Earth's axis tilts neither toward nor away from the Sun, but sideways to it, bringing equal hours of daylight and darkness to all latitudes. The spring equinox occurs around March 20th in the northern hemisphere, and the autumn equinox arrives around September 22nd, with the exact dates varying slightly year to year. The solstices mark maximum tilt, the longest and shortest days of the year, depending on hemisphere, occurring around June 21st and December 21st. These 4 points in the orbit structure the year into seasons, a rhythm that has remained stable throughout the time humans have observed the sky and recorded the patterns they witnessed. The orbital plane itself, the flat disk within which Earth travels, extends outward to include the other planets and defines what astronomers call the ecliptic. The Sun, Moon, and planets all stay close to this plane, appearing to move through a narrow band of constellations as seen from Earth. Ancient astronomers noticed this pattern and named the 12 constellations along this path the zodiac, recognizing that the Sun's apparent position shifted from one constellation to the next as the months progressed. They understood that something about Earth's position changed throughout the year, though the full picture of orbital motion would not emerge until Copernicus, Kepler, Galileo, and Newton developed the heliocentric model and the physics to explain it. Earth does not orbit alone, but carries the Moon along as a companion, and the two bodies actually orbit a common center of mass, called the barycenter. Because Earth outweighs the Moon by about 81 times, the barycenter sits much closer to Earth's center than to the Moon's, located roughly 1,700 kilometers below Earth's surface. Both Earth and Moon orbit this point as they travel together around the Sun, creating a slight wobble in Earth's path when plotted precisely. The Moon's own orbit around Earth takes approximately 27.3 days relative to the distant stars, a period called the sidereal month. And during this time, the Moon travels in a near circle at a distance averaging about 239,000 miles from Earth's center. As Earth follows its yearly circuit, our position relative to the background stars changes continuously, shifting our view of the cosmos beyond the solar system. In January, when Earth sits on one side of its orbit, we look out at night toward a particular region of the galaxy, seeing the constellations positioned there. 6 months later, in July, Earth has moved to the opposite side of its orbit, 93 million miles away from where it was, and the night side of the planet now faces a completely different direction in space. The constellations that were visible at midnight in January now sit behind the Sun in July, invisible in the daytime sky, while new constellations that were hidden in January daylight now appear overhead at midnight. This shifting perspective allows astronomers to observe stellar parallax, the apparent change in a star's position caused by viewing it from different points in Earth's orbit. Nearby stars appear to shift slightly against the background of far more distant stars as Earth moves from one side of its orbit to the other, tracing tiny ellipses on the sky that reflect our own orbital motion. The size of this ellipse depends on the star's distance, with closer stars showing larger parallax and distant stars showing shifts too small to measure easily. The first successful parallax measurements came in 1838 when Friedrich Bessel measured the distance to the star 61 Cygni, finally providing direct proof that Earth indeed orbits the Sun, and giving astronomers a method to measure stellar distances. The orbital motion continues with such regularity that we can predict Earth's position months or years in advance with extraordinary precision. The orbit has remained stable for billions of years, held in place by the Sun's gravity and by the vast emptiness of the solar system that allows the planets to travel unimpeded along their paths. Small perturbations occur as the other planet's gravity tugs on Earth slightly, particularly Jupiter, whose immense mass influences all the inner planets to some degree. But these effects average out over time and create only minor variations in the orbital parameters. The orbit we follow today matches closely the orbit Earth followed 10 million years ago, and will match closely the orbit Earth will follow 10 million years from now. This journey around the Sun, this 67,000 mile/hour circuit that takes 1 year to complete, adds to the rotational motion we explored earlier. Someone standing at the equator moves eastward at 1,000 miles/hour from rotation, and simultaneously moves along the orbital path at 67,000 miles/hour. Though the two motions point in different directions and combine in complex ways, depending on the time of day and year. But even this orbital speed does not represent the final layer of motion, because the Sun itself moves through the galaxy, and the entire solar system, all its planets and their moons, and the countless asteroids and comets that share this region of space, travels together on a far grander journey. The orbit around the Sun continues as it always has, but the Sun itself follows a much larger orbit around the center of the galaxy, and this motion dwarfs what we have examined so far. The Sun sits about 26,000 light-years from the center of the Milky Way galaxy, positioned roughly halfway out along one of the spiral arms in a region of moderate stellar density. 1 light-year equals approximately 6 trillion miles. The distance light travels in 1 year, moving at its constant speed of 186,000 miles per second. 26,000 of these distances stack together to span the gap between our solar system and the bright, crowded core of the galaxy, where hundreds of billions of stars orbit a supermassive black hole. Out here, in our suburban neighborhood, the stars spread farther apart, and the space between them grows darker and quieter than the brilliant central regions. The Sun orbits this distant center at a speed of about 450,000 miles per hour, roughly 200 kilometers every second, nearly 7 times faster than our orbital speed around the Sun itself. This tremendous velocity carries the entire solar system around the galactic center in a motion that takes approximately 230 million years to complete 1 full circuit. Astronomers sometimes call this period a cosmic year or a galactic year, a timescale so immense that it dwarfs all of human history and most of Earth's geological record. The Sun has completed only about 20 orbits since it formed 4.6 billion years ago, and life on Earth has existed for perhaps 15 or 16 of those great circuits around the galaxy. To comprehend the duration of 1 galactic year requires connecting it to events on Earth across deep time, anchoring the abstract number to familiar planetary history. 230 million years ago, Earth was a very different world than the one we know today. The continents had assembled into the supercontinent Pangaea, a single vast landmass surrounded by the global ocean Panthalassa, with no Atlantic Ocean yet existing between the Americas and Europe and Africa. The climate ran generally warmer and drier than today, with vast deserts covering the interior of the supercontinent, far from any coastline. Life had recovered from the devastating Permian extinction that occurred about 20 million years earlier, the worst mass extinction in Earth's history, which had eliminated more than 90% of marine species and about 70% of terrestrial vertebrate species. Dinosaurs had just begun to appear in the fossil record around this time, small early forms that would eventually diversify into the tremendous variety of species that dominated the Mesozoic era. The first true dinosaurs emerged in the Triassic period, roughly 230 to 240 million years ago, just as the Sun occupied nearly the same position in its galactic orbit that it occupies today. Mammals existed too, though only as small, shrew-like creatures living in the shadows of the larger reptilian life forms, their descendants not yet imagining they would one day inherit the Earth. The oceans teemed with ammonites, marine reptiles, and fish, while on land, the first coniferous forests began to spread. Seed-bearing plants that did not require water for reproduction, the way earlier ferns and mosses had. Since that time, the Sun has traveled completely around the galaxy and returned approximately to where it was, completing 1 full orbit, while Earth itself orbited the Sun 230 million times. During this immense period, Pangaea broke apart into the continents we recognize today, which drifted to their current positions through the slow process of plate tectonics. The Atlantic Ocean opened between the separating land masses. The Pacific Ocean shrank correspondingly, and mountain ranges rose and eroded away in cycles. The dinosaurs rose to dominance, ruled for over 150 million years, and then vanished in the extinction event 66 million years ago when an asteroid struck the Yucatan Peninsula. Mammals diversified to fill the ecological niches the dinosaurs left empty. And eventually, only a few million years ago, humans emerged in Africa and began their own brief journey through time. The galactic orbit places our solar system not in a fixed path like Earth's nearly circular route around the Sun, but in an orbit that bobs up and down relative to the galactic plane. The Milky Way forms a disk shape, with most stars concentrated in a flat region about 1,000 light-years thick at our distance from the center, though the thickness varies at different radii. The Sun currently sits slightly north of the midplane, about 90 light-years above it, and moves in a path that oscillates up and down through the plane in a gentle wave. This vertical motion takes roughly 30 to 35 million years to complete one full cycle from north to south and back to north again. A rhythm that carries us through regions of different stellar density as we rise above and sink below the densest part of the disk. As the Sun passes through the galactic plane, it moves through regions with slightly higher concentrations of gas and dust, regions where molecular clouds occasionally condense to form new stars, and where the density of matter increases compared to the space above or below the plane. Some researchers have proposed that these passages through the plane might influence Earth through increased comet impacts, as the denser regions could gravitationally perturb the distant Oort cloud and send more comets falling toward the inner solar system. The evidence for such periodic impacts remains uncertain and debated, but the idea illustrates how our galactic motion might have subtle consequences even for life on Earth across deep time. The speed of 450,000 miles per hour represents our velocity relative to the galactic center, measured by tracking the Doppler shift of radio emissions from the center and from objects orbiting near it. The galactic center itself emits strongly at radio wavelengths, particularly from a source called Sagittarius A star, the radio signature of the supermassive black hole that sits at the Milky Way's heart. This black hole contains about 4 million times the Sun's mass, and its gravity anchors the entire rotation of the galaxy. Though most of the gravitational pull we experience comes from the combined mass of all the stars and dark matter closer to the center than we are. The orbital period of 230 million years emerges from dividing the circumference of our orbit by our orbital speed, a simple calculation once the distance and velocity are known. The circumference at our orbital radius equals about 163,000 light-years, an enormous loop through space that we travel at steady speed, unlike Earth's orbit around the Sun, which we can observe changing throughout a human lifetime and which our ancestors tracked across centuries. The Sun's galactic orbit proceeds so slowly that stellar positions barely shift even across many human generations. The nearest stars do show measurable proper motion, gradual changes in their positions over decades and centuries. But these motions result mostly from those stars' individual movements through the galaxy, rather than from our shared orbital motion around the center. From a vantage point far outside the Milky Way, looking at the galaxy from a distance of millions of light-years, our Sun would appear as one unremarkable star among hundreds of billions. The galaxy itself would show as a graceful spiral, arms of bright young stars and glowing gas winding outward from the central bulge in a pattern familiar from photographs of other spiral galaxies. Locating our sun in that image would require knowing precisely where to look, finding one specific yellow star about 2/3 of the way out from the center, positioned within one of the minor spiral arms. The sun would be moving along its orbit, but would appear essentially stationary in such a view, the motion imperceptible over timescales of thousands or even millions of years from such cosmic distance. Closer inspection from this imaginary outside perspective would reveal that the sun has moved since the last time it occupied this position in the galaxy, because the orbit does not close precisely into a perfect ellipse, the way planetary orbits do. The gravitational field of the galaxy differs fundamentally from the field around the sun, distributed across billions of stars and vast clouds of dark matter, rather than concentrated in one central mass. This distributed gravity creates an orbit that processes and wobbles slightly, so that completing one circuit does not return the sun to exactly the same coordinates, but to a position slightly shifted from before. Over many orbits, the path traces a complex rosette pattern rather than a simple closed loop, wandering slightly inward and outward over time while maintaining an average distance from the center. The journey continues, as it has for billions of years, the sun and all its planets gliding through the space between stars at nearly 500,000 miles per hour. The motion feels no different from stillness, as there is nothing to push against in the vacuum of space, no reference point to show we are moving, no sensation of speed at all. But the journey proceeds, bringing us through different regions of the galaxy, past stars that were far away in previous orbits, and towards stars we will approach in future circuits. The slow cosmic waltz continuing through time spans that make human civilization appear as the briefest flicker. And this motion, vast as it is, takes place within a particular region of the galaxy's structure, a location that shapes what we see when we look outward at night, and that influences the environment our solar system passes through on its long journey around the galactic heart. The Milky Way organizes itself into structure, not simply a uniform disk of stars, but a complex architecture of spiral arms and spurs that wind through the galaxy's disk like a slowly turning pinwheel. These arms contain higher concentrations of gas, dust, and young bright stars compared to the regions between them, creating the luminous patterns visible when we view other spiral galaxies from outside. Our own galaxy's structure remained mysterious for much longer than distant galaxies. Because we sit inside the disk, looking outward, our view blocked in many directions by intervening dust, our perspective limited by our location within the pattern we are trying to map. The major spiral arms of the Milky Way include the Perseus arm, located inward from our position toward the galactic center, and the Sagittarius arm, positioned between us and the center on the opposite side of the galaxy from our perspective. The outer arm lies beyond our position, farther from the center, and several other major arms wind through the disk at different radii. Mapping these structures required decades of careful observation, using radio telescopes that can penetrate the dust clouds blocking visible light, allowing astronomers to detect the hydrogen gas that concentrates in the arms and trace their positions through the galaxy. The full structure still holds uncertainties, particularly regarding how many major arms exist and how tightly they wind, because our inside view makes creating a complete map extraordinarily difficult. The Sun resides not in one of the major arms, but in a smaller structure called the Orion Spur, sometimes called the Orion Arm, a minor arm or spur that branches off between the Perseus and Sagittarius arms. This feature stretches about 10,000 light-years in length and about 3,000 light-years in width. A significant structure, but smaller than the major arms that define the galaxy's overall spiral pattern. The spur contains enough gas and ongoing star formation to show up clearly in observations, but does not rank as one of the primary arms that wind from the inner galaxy outward to the edge. Within this spur, the Sun occupies a relatively quiet region called the local bubble, a cavity of low-density gas about 1,000 light-years across that formed when multiple supernovae exploded in our region of space several million years ago. These explosions blew away most of the interstellar gas and dust, creating a bubble of hot, tenuous plasma surrounded by denser material. The Sun sits near the edge of this bubble, in a small, denser region called the local fluff, or local interstellar cloud, a patch of slightly higher density within the larger cavity. This immediate neighborhood provides the material our solar system currently moves through, though the density remains extremely low. Only about 1/10 of an atom per cubic centimeter, compared to the billions of trillions of molecules in each cubic centimeter of air we breathe. The spiral arms themselves represent not fixed structures of stars moving together, but density waves, patterns that persist while individual stars move through them at their own speeds. Stars orbit the galaxy at different rates depending on their distance from the center, creating differential rotation where inner stars complete orbits faster than outer stars. If the arms were simply groups of stars moving together, differential rotation would wind them tighter and tighter until they wrapped around the galaxy many times, destroying the spiral pattern. Instead, the arms persist as waves of slightly higher density, regions where stars and gas concentrate temporarily before moving on. Much like cars, bunch up in slow-moving regions of a traffic wave on a highway, while individual cars pass through the dense region and continue at their own speeds. As the Sun orbits the galaxy, it passes through these arms periodically, entering regions of higher stellar density and greater concentrations of gas and dust before emerging into the quieter regions between arms. The journey through an arm takes roughly 10 million years, given the arm's width and our orbital speed. And the time between arm crossings depends on the spacing between arms and the slight difference between our orbital speed and the speed at which the density wave pattern itself rotates. Current estimates suggest we cross a major spiral arm every 80 to 100 million years, though the exact timing remains uncertain due to uncertainties in both the arm locations and the pattern speed. When the solar system passes through a spiral arm, the local environment changes in subtle but measurable ways. The density of interstellar material increases, meaning the solar system plows through more gas and dust than usual, though the densities remain far lower than even the best vacuum achievable in laboratories on Earth. The rate of nearby supernovae might increase because the arms contain more massive young stars, which live fast and die in spectacular explosions. The influx of cosmic rays, high-energy particles produced by supernovae and other energetic events, could rise during arm passages, potentially affecting Earth's atmosphere and even climate through complex mechanisms that researchers continue to study and debate. Looking inward from our position toward the galactic center, we see the Perseus arm as a bright band of stars and glowing gas arcing across the sky, contributing to the luminous glow of the Milky Way, visible on dark nights. Beyond the Perseus arm lies the Sagittarius arm, and beyond that, the central bulge itself, a dense concentration of older stars surrounding the supermassive black hole. The center lies in the direction of the constellation Sagittarius as seen from Earth, hence the name of the nearby spiral arm. And the richest star fields in the night sky appear in that region, where we look through multiple layers of galactic structure toward the crowded core. Looking outward from our position, away from the galactic center, we see sparser regions and the outer arm in the distance, with fewer layers of stars between us and the edge of the galaxy. The view in this direction shows less concentration of bright stars, a dimmer band of the Milky Way, compared to the view toward the center, reflecting the geometry of our position within the disk. The galactic north and south directions, perpendicular to the disk, open onto the vast intergalactic space beyond. And looking in these directions, we see fewer foreground stars and can observe distant galaxies without the obscuration of the Milky Way's dense disk blocking the view. Our position in the Orion Spur places us in what might be considered galactic suburbs, a region neither in the crowded urban core nor in the sparse rural outskirts. The stellar density here provides enough neighbors that our night sky fills with stars, but remains sparse enough that close encounters with other stars happen only rarely, on average every few million years. This intermediate location may have contributed to the stability of Earth's environment over billions of years, keeping us away from the more violent central regions where supernovae occur frequently and gravitational interactions perturb planetary systems, while also avoiding the sparse outer regions where heavy elements needed for rocky planets and life might be less abundant. The structure we inhabit changes slowly as we orbit, the solar system gradually shifting position within the Orion Spur and relative to the major arms as our orbit continues. The spur itself rotates at a slightly different speed than the Sun, so our position within it drifts over tens of millions of years. And the crossings of major arms punctuate the journey with periods of denser environment between longer stretches of traversing the quieter inter-arm regions. This variation creates a slow rhythm to our galactic journey, a pace of environmental change that operates on timescales far longer than species evolution, but potentially relevant to the broadest patterns in Earth's geological and biological history. And while the Sun follows its orbit through this structured galaxy, carrying its planets along the ancient path, the motion does not proceed in isolation from neighboring stars. Each star in the region has its own orbit around the galactic center. Each moves at its own individual speed and direction. And when we measure our motion against our stellar neighbors, rather than against the distant center, another layer of movement emerges, revealing how the Sun wanders through the local stellar population, even as it orbits the galaxy as a whole. The stars near the Sun move through the galaxy on their own independent paths, each following an orbit determined by where it formed and how gravitational interactions have influenced its trajectory over millions and billions of years. These individual motions mean that the stellar neighborhood constantly changes, with stars that are close to us today gradually drifting away, while other stars from more distant regions approach and eventually pass nearby. The Sun participates in this wandering, moving through the local population of stars in a direction and at a speed that differs slightly from the average motion of stars in our region, creating what astronomers call the solar peculiar velocity. The local standard of rest represents the average motion of stars in our neighborhood around the galactic center, a sort of mean velocity that describes how stars at our distance from the core typically move. This standard of rest rotates around the galactic center at roughly the same speed we discussed earlier, the 450,000 miles per hour that characterizes our orbital motion. Individual stars deviate from this average, moving a bit faster or slower and tilted in different directions relative to the purely circular path. And these deviations create the peculiar velocities, the differences between each star's actual motion and the local average. The Sun's peculiar velocity amounts to about 43,000 miles per hour, roughly 20 kilometers per second, measured relative to the local standard of rest. This might seem like a small fraction of our overall orbital speed, less than 10% of the total, but it represents a significant motion relative to our immediate neighbors. Breaking down this velocity into components, the Sun moves slightly inward toward the galactic center compared to the average star at our position, slightly faster in the direction of galactic rotation than average, and somewhat upward out of the galactic plane compared to the typical motion, creating a three-dimensional drift through the local stellar population. The direction we are heading, the point in the sky toward which the Sun's peculiar motion carries us, is called the solar apex. This point lies in the constellation Hercules, near the bright star Vega, positioned in the northern sky as seen from Earth. The opposite point, the direction from which we are moving away, is called the solar antepex, located in the constellation Columba in the southern sky. These points remain roughly fixed relative to the distant stars over human timescales, though they drift slowly over millions of years as the Sun's peculiar velocity changes in response to gravitational perturbations from passing stars and giant molecular clouds. Nearby stars show their own peculiar velocities when measured carefully, each moving in its own particular direction at its own speed through the local stellar neighborhood. Barnard's star, located about 6 light-years from the Sun, holds the record for the highest proper motion of any known star, moving across our sky at about 10.3 seconds of arc per year. This rapid motion results from both its relative proximity and its substantial, peculiar velocity, carrying it southward across the sky at a speed that will bring it closer to the Sun over the next several thousand years before it passes by and begins receding into the distance. Proxima Centauri, currently the closest star to the Sun at just over 4 light-years away, will not hold that title forever. Its own peculiar motion carries it on a trajectory that will eventually take it farther from us. And in about 27,000 years, it will be replaced as our nearest neighbor by another star passing through the region. Proxima orbits the binary star system Alpha Centauri A and B at a considerable distance, taking over 500,000 years to complete. One orbit around the pair, and this orbital motion combines with its peculiar velocity through the galaxy to create a complex path through space. Close encounters between stars happen rarely, but inevitably over millions of years, as different stars' paths happen to intersect. A close approach means passing within a light year or two of the Sun, close enough that the passing star's gravity might disturb the distant comets in the Oort cloud. The spherical shell of icy bodies that surrounds the solar system at distances from thousands to tens of thousands of astronomical units. Such encounters could send showers of comets falling toward the inner solar system, increasing the impact rate on planets for a period of time before the influx fades as the perturbed comets either collide with planets, are ejected from the solar system, or settle into new orbits. Analyzing the motions of nearby stars allows astronomers to calculate when such encounters occurred in the past and when they might happen in the future. Roughly 70,000 years ago, a pair of small stars called Schultz's star passed within about 0.8 light-years of the Sun, well within the outer Oort cloud. The stars were red dwarfs, low-mass objects much smaller and dimmer than the Sun, and their passage likely perturbed some comets, but probably did not cause any significant effect on Earth, given the low mass of the intruders and the distance of closest approach. This encounter happened when modern humans were already present on Earth. Anatomically modern people who would have seen these stars as faint reddish points moving slowly across the night sky had they looked in the right direction and noticed the gradual motion. Looking forward in time, the star Gliese 710 is predicted to pass within about 0.2 light-years of the Sun in about 1.3 million years, a much closer approach than Scholz's star. Gliese 710 is an orange dwarf, somewhat smaller and cooler than the Sun, but more massive than the red dwarfs that passed previously. And its close passage will almost certainly disturb the Oort cloud significantly. The resulting comet shower might increase impact rates in the inner solar system for a period of time afterward, though predicting the exact effects remains difficult, given the many uncertainties about the Oort cloud's structure and population. The changing stellar neighborhood means that the stars we see in our night sky today differ from the stars our distant ancestors would have seen if they could have observed with the same clarity millions of years ago. Over timescales of millions of years, the familiar constellations slowly distort and change shape as each star moves according to its own peculiar velocity, shifting positions relative to one another. Stars that appear close together in the sky because they lie in the same direction from Earth might actually be at very different distances, and they are almost certainly moving in different directions. So the apparent grouping is temporary and will dissolve over time. The measurement of stellar motions requires patient observation over years and decades, comparing the positions of stars at different times to detect the tiny shifts called proper motion. This apparent motion across the sky combines the star's peculiar velocity through space with the effects of our own sun's peculiar motion, creating a complex pattern that astronomers must untangle to understand each star's true three-dimensional velocity. The radial velocity, motion toward or away from us along the line of sight, comes from measuring Doppler shifts in the star's spectrum, while the tangential velocity, motion across the line of sight, comes from proper motion measurements combined with distance estimates. Combining all these measurements for many stars in the solar neighborhood creates a three-dimensional map of local stellar motions, revealing the complex swirl of stars moving through space in all directions. Some stars move roughly along with the local standard of rest, participating in orderly galactic rotation, while others have higher peculiar velocities that carry them on more eccentric paths. The oldest stars often show the highest peculiar velocities because they have had more time to accumulate gravitational perturbations from encounters with giant molecular clouds and other concentrations of mass. While younger stars often move more uniformly because they recently formed from the same rotating disk of gas and have not yet had time to develop large velocity deviations. The Sun's peculiar motion of 20 kilometers per second places it somewhere in the middle of the range, shown by nearby stars, neither moving particularly slowly nor particularly fast compared to its neighbors. This moderate peculiar velocity suggests a typical history of gravitational interactions over the Sun's 4.6 billion year lifetime, with no extraordinary close encounters or other events that would have dramatically altered the solar system's trajectory through the galaxy. The motion toward the solar apex in Hercules continues steadily, carrying us about 16 astronomical units closer to Vega each year, a distance equal to roughly twice the Sun-Neptune separation. Though Vega itself also moves, so the actual approach rate differs from this simple calculation. And this wandering through the local stellar population happens against the backdrop of the larger galactic rotation, the individual peculiar velocities of stars superimposed on their shared orbital motion around the center. The combination creates a picture of the galaxy not as a rigid structure, but as a dynamic system where every star moves on its own path, while the overall pattern of rotation and spiral structure persists across billions of years. These individual motions, when averaged across enormous numbers of stars, reveal something fundamental about how the galaxy rotates. And that rotation holds a profound mystery that reshaped our understanding of the universe. The Milky Way rotates, its hundreds of billions of stars orbiting the common center in a vast, slow wheel that has turned for over 13 billion years. But the rotation does not proceed the way a solid object rotates, with all parts turning together at the same rate. Instead, the galaxy exhibits differential rotation, with stars at different distances from the center, completing their orbits at different rates, inner regions moving faster and outer regions moving slower in terms of orbital period, creating a pattern more complex than the simple spin of a wheel or disk. At the very center of the galaxy, within the innermost regions where the supermassive black hole dominates the gravitational field, stars orbit at tremendous speeds, completing circuits in just a few years or decades. Moving outward from the center, the orbital period increases, with stars taking longer and longer to complete one revolution around the galactic core. At our distance of about 26,000 light-years, the orbital period reaches 230 million years, as we have seen. Farther out still, at distances of 40 or 50,000 light-years, the orbital period extends to 500 million years or more, with stars in the outer halo taking even longer to complete their immense circuits. This differential rotation arises naturally from the laws of orbital mechanics, first described by Johannes Kepler and later explained by Isaac Newton's law of gravitation. For objects orbiting a central mass, the orbital period increases with distance according to Kepler's third law, which states that the square of the orbital period is proportional to the cube of the orbital radius. This relationship holds precisely when all the mass concentrates at the center, as it does, essentially, for planets orbiting the Sun. And it holds approximately for stars orbiting a galaxy, when most of the mass interior to the star's orbit sits closer to the center than the star itself. Based on the distribution of visible stars and gas in the Milky Way, astronomers in the early 20th century predicted how orbital speeds should vary with distance from the galactic center. They expected the speed to increase in the inner regions where most of the visible mass concentrates, reach a maximum somewhere in the middle regions, and then decline in the outer parts according to Kepler's laws, dropping off in proportion to 1 over the square root of the distance for stars orbiting beyond most of the galaxy's mass. This prediction formed a rotation curve, a graph of orbital velocity versus distance from the center, showing the expected shape based on the visible matter. When astronomers actually measured the rotation curve by observing the velocities of stars and gas clouds at different distances using Doppler shifts, they found something unexpected. The inner parts of the curve matched predictions reasonably well, with velocity increasing as expected in regions where mass continues to accumulate with increasing radius. But in the outer regions, where the velocity should have declined according to Kepler's laws, the rotation curve stayed flat instead, maintaining roughly constant orbital speed out to the largest distances that could be measured. Stars and gas far from the galactic center moved much faster than the visible matter could explain, orbiting at speeds that should have flung them out of the galaxy entirely, unless far more mass existed than could be seen. The discrepancy appeared not only in the Milky Way, but in every spiral galaxy where the rotation curve could be measured accurately. Galaxy after galaxy showed the same pattern: flat rotation curves in the outer regions, where declining curves were expected, indicating that every spiral galaxy contains far more mass than its visible stars and gas account for. The amount of additional mass needed to explain the observations proved substantial, roughly 5 to 6 times more mass than exists in visible form, distributed in an extended halo surrounding each galaxy and reaching far beyond the visible disk. This invisible mass became known as dark matter, a placeholder name describing matter that does not emit, absorb, or reflect light at any wavelength, making it completely invisible to telescopes, but detectable through its gravitational effects. The dark matter in our galaxy forms an approximately spherical halo extending perhaps 500,000 light-years from the center, far larger than the visible disk, which spans only about 100,000 light-years. The halo contains most of the galaxy's total mass, with the visible stars and gas making up only a small fraction of what actually exists, and the gravity of this dark halo holds the galaxy together and shapes the flat rotation curve we observe. The nature of dark matter remains one of the great unsolved mysteries in physics and astronomy. Observations tell us it exists, and roughly how it distributes itself through galaxies and galaxy clusters. But they do not reveal what particles constitute it, or how those particles interact with ordinary matter beyond gravitational attraction. The dark matter does not consist of normal atoms made of protons and neutrons, because we can account for all the ordinary matter through other observations and calculations, and the total falls far short of what the rotation curves require. Instead, dark matter must be something else entirely, perhaps exotic particles predicted by extensions to the standard model of particle physics. Particles that have mass and therefore gravity, but interact only very weakly, or not at all with electromagnetic radiation. Despite its invisibility, dark matter plays a crucial role in galaxy formation and structure. Computer simulations show that galaxies could not have formed without dark matter, because the ordinary matter alone would not have clumped together quickly enough under its own gravity to create the structures we see. The dark matter formed the scaffolding, concentrating first into halos through gravitational collapse during the early universe, and ordinary matter then fell into these dark matter wells and condensed to form stars and galaxies. The distribution of dark matter determined where galaxies formed and how they evolved, making it fundamental to the cosmic architecture, despite its invisible nature. The flat rotation curve has another consequence for our earlier discussion of the Sun's orbital speed. The velocity we described, 450,000 miles per hour around the galactic center, includes the effects of dark matter. Without the dark matter halo, the visible mass of the galaxy would generate much weaker gravity at our location, and we would orbit significantly slower, completing each circuit in less time. The dark matter's presence speeds our orbit and lengthens our orbital period compared to what visible matter alone would produce, shaping the journey our solar system takes through the galaxy. Differential rotation creates consequences for the spiral structure we explored in the previous part. If the spiral arms consisted of fixed groups of stars rotating together, differential rotation would wind them progressively tighter, wrapping them many times around the galaxy within a few orbits. The fact that we observe spiral galaxies with clear, open spiral patterns, not tightly wound structures, indicates that the arms cannot be material features rotating as solid objects. Instead, as mentioned earlier, the arms appear to be density waves, patterns that rotate at their own speed, distinct from the orbital speeds of individual stars, maintaining their structure even as stars pass through them at different rates. The density wave theory, developed in the 1960s, explains how spiral arms persist despite differential rotation. The waves represent regions where stars and gas bunch up temporarily, much like traffic waves on a highway where cars slow down and cluster together before accelerating and spreading out again. The pattern rotates at a fixed rate, called the pattern speed, while individual stars orbit at their own speeds determined by their distance from the center. Stars catch up to the density wave from behind, slow down slightly as they pass through the denser region, and then accelerate again as they emerge, maintaining the pattern even though no individual star stays in the arm permanently. This mechanism allows spiral structure to persist for billions of years, while the galaxy rotates differentially. The arms maintained by the gravitational effects of the density enhancements themselves, which attract nearby matter and reinforce the pattern. The exact origin of the density waves remains debated, with tidal interactions from companion galaxies, internal instabilities in the disk, and other mechanisms all potentially contributing. The Milky Way's spiral pattern likely has multiple causes operating together to create and sustain the structure we inhabit. The rotation of the galaxy provides a sense of time and rhythm to the cosmos, a great slow turning that has continued since the galaxy formed over 13 billion years ago. The Sun has completed approximately 20 orbits in its lifetime, each one carrying it through the same general path, but with slight variations as gravitational perturbations and the changing mass distribution of the galaxy nudge the orbit this way and that. The rotation continues today as it did billions of years ago, and it will continue billions of years into the future. The galaxy turning until eventually it merges with other galaxies and transforms into something new. And this entire rotating structure, the whole Milky Way, with its spiral arms and dark matter halo and hundreds of billions of stars, does not sit stationary in space, but moves through the universe as part of a larger cosmic dance. The Milky Way does not journey through the universe alone, but belongs to a family of galaxies called the Local Group, a gravitationally bound collection spanning about 10 million light-years across. This group contains two large spiral galaxies, the Milky Way and Andromeda, along with one smaller spiral called the Triangulum Galaxy, and dozens of smaller dwarf galaxies that orbit the larger members like moons around planets. The entire collection moves through space together, while its members also move relative to one another, creating a complex gravitational dance that has played out for billions of years and will continue for billions more. Andromeda, also called Messier 31 or M31, sits about 2.5 million light-years from the Milky Way, making it the nearest large galaxy to our own. It spans roughly twice the diameter of the Milky Way and contains about 1 trillion stars compared to our 200 to 400 billion, making it the dominant member of the Local Group by mass. On dark nights, far from city lights, Andromeda appears as a faint smudge in the constellation it is named for, visible to the naked eye as the most distant object humans can see without optical aid. Light that has traveled for 2.5 million years before reaching our eyes. The two galaxies do not sit still relative to each other, but approach at a speed of about 250,000 miles per hour, roughly 110 kilometers per second. This closing speed emerges from measurements of Andromeda's Doppler shift, which shows the galaxy blue shifted, meaning its light waves compress slightly as it moves toward us. The approach has continued for billions of years, gravity pulling the two large galaxies together across the vast gulf between them. And it will continue into the future until eventually the galaxies collide and merge into a single larger structure. The merger will not happen soon by human standards, with current estimates placing the first close passage about 4 billion years from now. At that time, the two galaxies will swing past each other in a complex gravitational interaction, their shapes distorting as tidal forces stretch and deform the stellar disks. The galaxies will not collide in the sense of stars crashing into each other, because the space between stars is so vast that stellar collisions remain extraordinarily unlikely, even when two galaxies interpenetrate. Instead, the stars will pass through each other like two swarms of bees occupying the same space briefly, their paths altered by the changing gravitational field, but rarely approaching close enough to actually collide. After the first passage, the two galaxies will separate briefly, their momentum carrying them apart, before gravity reverses the motion and pulls them back together for a second passage. This process may repeat several times, each passage removing energy from the system through a complex mechanism involving the gravitational slingshot effects of close encounters and the excitation of density waves. Eventually, after perhaps another 1 billion or 2 years of these interactions, the galaxies will settle into a single merged structure, likely an elliptical galaxy containing all the stars from both spirals, but with the ordered disk structure disrupted and destroyed by the violent gravitational interactions. From Earth's perspective, if Earth still exists 4 billion years from now, and if humans or their descendants are present to watch, the approach will transform the night sky slowly over millions of years. Andromeda will gradually grow larger, taking up more of the sky, shifting from a small faint patch to a clearly visible elongated glow, eventually filling a substantial portion of the sky as it approaches. During the close passages, the galaxy will dominate the heavens, appearing much larger than the Moon. Its spiral structure, potentially visible to the naked eye, if enough star formation lights up the arms during the interaction. The Milky Way's disk will also be visible from Earth as a band completely encircling the sky, because the disruption might tilt Earth's position relative to our current plane, though such details remain highly uncertain. The Sun itself will likely survive the merger intact, along with its planets, if they remain bound to the Sun at that distant time. The solar system will be flung into a different orbit around the merged galaxy's center, possibly moving much closer to the core or much farther out, depending on the particular gravitational encounters that occur during the chaotic merger process. The night sky will look completely different, with unfamiliar stars nearby and the galactic center in a new position, a transformed cosmos for any beings that might witness it. Other members of the local group include the Triangulum Galaxy, M33, which sits about 3 million light-years from the Milky Way and may be a satellite of Andromeda, or maybe an independent member of the group. Triangulum contains perhaps 40 billion stars, much smaller than either of the two dominant spirals, and it too moves through the local group on a path that may eventually bring it into interaction with Andromeda and the Milky Way, adding its mass to the eventual merger product. The Large Magellanic Cloud and Small Magellanic Cloud orbit the Milky Way at distances of about 160,000 and 200,000 light-years respectively, close enough that they appear as prominent features in the southern sky for observers in Earth's southern hemisphere. These irregular dwarf galaxies contain billions of stars, and ongoing star formation and their gravitational interaction with the Milky Way has drawn out long streams of gas, called the Magellanic Stream, material stripped from the clouds and stretched across the sky in a vast arc. The clouds orbit the Milky Way in a complex path that will eventually bring them closer, and they may eventually be absorbed into the larger galaxy, their stars incorporated into the Milky Way's halo. Dozens of smaller dwarf galaxies surround the Milky Way and Andromeda, tiny systems containing millions or billions of stars rather than hundreds of billions. These satellites orbit their parent galaxies much as the Magellanic Clouds orbit the Milky Way, held in place by gravity and slowly losing mass to tidal stripping that pulls their outer stars away. Many of these dwarfs have been discovered only in recent decades as surveys become sensitive enough to detect the faint concentrations of stars, and more likely remain undiscovered, hidden in the glare of the Milky Way or positioned in difficult-to-observe regions of the sky. The local group as a whole has a center of mass, a point in space around which all the member galaxies orbit, determined by the mass and position of each galaxy. This center of mass sits somewhere between the Milky Way and Andromeda, closer to Andromeda because of its greater mass. The local group remains gravitationally bound, meaning its members will not escape into the expanding universe, but will remain together, continuing their gravitational interactions until the final merger creates one or perhaps two large elliptical galaxies containing all the matter currently spread across dozens of separate systems. The diameter of the local group, roughly 10 million light-years, places it among the smaller galaxy groups in the universe. Larger groups and clusters contain hundreds or even thousands of galaxies with incomparable volumes, creating much denser environments where galaxy mergers happen frequently and the hot gas between galaxies glows brightly in X-rays. The local group's modest size creates a relatively quiet environment where mergers proceed slowly over billions of years, and individual galaxies maintain their identities for extended periods before finally coalescing. The motion of the Milky Way within the local group combines its orbit around the group's center of mass with the overall motion of the entire group through the larger universe. Separating these components requires careful measurement of many galaxies' positions and velocities to determine the group's mean motion and then calculate each galaxy's deviation from that mean. The Milky Way moves toward Andromeda, as we have seen, but both galaxies also participate in a larger collective motion that carries the entire local group through space at far higher speed than the internal motions between members. This larger motion arises from gravity on much grander scales, the pull of structures far beyond the local group that dominate the cosmos at the largest distances we can observe. The local group moves through the universe at approximately 1.3 million miles per hour, roughly 600 kilometers every second, pulled by gravitational forces from massive structures that lie tens and hundreds of millions of light years beyond our small collection of galaxies. This motion represents the largest scale movement we experience, the sum of all the cosmic motions added together in a particular direction through space. It dwarfs every other velocity we have discussed, exceeding our galactic orbital speed by a factor of 3 and our solar orbital speed by a factor of nearly 20, carrying not just the Earth or the solar system or the Milky Way, but dozens of galaxies together through the expanding universe. The direction of motion points roughly toward a region of sky in the constellations Hydra and Centaurus, an area containing the Virgo supercluster, a massive collection of galaxy groups and clusters spanning about 110 million light-years. The Virgo cluster sits at the center of this supercluster, a concentration of over 1,000 large galaxies, along with countless smaller ones, located about 65 million light-years from the local group. The gravity of this enormous mass concentration pulls on everything in the surrounding region, including our local group, contributing to our motion toward it, though not accounting for all of the observed velocity. Beyond the Virgo supercluster lies an even more massive structure called the Great Attractor, a region of space containing an enormous concentration of mass, centered about 250 million light-years from the Milky Way. The Great Attractor was identified in the 1970s and 80s, when astronomers measured the peculiar velocities of many galaxies and found a systematic flow pattern indicating motion toward a particular region of sky. The structure itself remained difficult to observe directly because it sits behind the zone of avoidance, the region of sky where the Milky Way's own disk blocks our view with dense clouds of dust and gas, obscuring whatever lies in that direction. Observations using wavelengths that penetrate the dust, particularly infrared and radio observations, eventually revealed a massive concentration of galaxy clusters in the region of the Great Attractor. The structure contains tens of thousands of galaxies, organized into clusters and superclusters, with a total mass equivalent to tens of thousands of Milky Way galaxies, creating a gravitational pull strong enough to influence the motion of galaxies and galaxy groups across hundreds of millions of light years. The Milky Way, the local group, the Virgo supercluster, and countless other structures all flow toward the Great Attractor, pulled by its immense gravity. But the Great Attractor itself moves, pulled by even larger structures farther beyond. The Shapley supercluster sits about 650 million light-years from the Milky Way in roughly the same direction as the Great Attractor, and this supercluster represents one of the largest mass concentrations in the nearby universe, containing more than 8,000 galaxies with a total mass perhaps 50,000 times that of the Milky Way. The gravity of the Shapley supercluster pulls on the Great Attractor region and on everything between us and it, contributing to the overall flow pattern that carries galaxies through space along preferred directions. These structures and motions fit into a larger cosmic architecture called the cosmic web, a network of filaments, walls, and voids that extends throughout the observable universe. Galaxies and galaxy clusters concentrate along filaments, long, narrow structures that can stretch for hundreds of millions of light years, creating a web-like pattern when mapped in 3 dimensions. The filaments connect at nodes where multiple strands meet, creating massive galaxy clusters at these intersections. Between the filaments lie vast voids, regions containing very few galaxies, where the density of matter falls far below the cosmic average. The local group sits on a filament that connects to the Virgo supercluster, flowing along this cosmic highway toward denser regions. The motion we experience represents our flow along the filament, pulled by the mass concentrations ahead, and also fleeing to some degree from the underdense void regions behind, where the below-average gravity allows us to fall away toward regions of stronger gravitational attraction. This flow happens throughout the universe, with galaxy groups and clusters streaming along filaments at hundreds of kilometers per second, creating what astronomers call cosmic flows, or bulk flows, large-scale coherent motions involving thousands of galaxies moving together. The cosmic web, formed through gravitational instability in the early universe, tiny density variations present shortly after the Big Bang, growing over billions of years as regions slightly denser than average attracted more matter, while regions slightly less dense lost matter to their surroundings. Dark matter played a crucial role in this process, clumping first because it does not interact with radiation and could collapse under its own gravity without resistance. Ordinary matter then fell into the dark matter concentrations, condensing to form stars and galaxies along the filaments where dark matter had already created the underlying structure. The pattern emerged gradually, with small clumps forming first, and then merging hierarchically into larger and larger structures over cosmic time. The process continues today, with galaxy clusters still forming through the merger of smaller groups, though the expansion of the universe works against gravity at the largest scales, causing the most distant structures to recede from one another faster than their mutual gravity can pull them together. Only structures already gravitationally bound, like the local group or the Virgo cluster, remain connected and will continue collapsing and merging while the space between separate clusters expands. The velocity of 1.3 million miles per hour represents the combination of all our motions when measured in the specific direction toward the Great Attractor and Shapley supercluster. In other directions, the various motions add and subtract differently, producing smaller net velocities or even producing motion in different directions. The number captures a particular perspective, the speed in the direction of our fastest motion through the universe, and it includes Earth's orbital motion around the Sun's orbital motion around the galactic center, the Milky Way's motion through the local group, and the local group's motion through the cosmic web, all added together vectorially. This motion was not always known, and discovering it required developing methods to measure velocities accurately across vast cosmic distances. The cosmic microwave background radiation provided a key tool for measuring our absolute motion through the universe, revealing a dipole pattern in the microwave sky that directly indicates our velocity relative to the ancient light filling space. But understanding what this motion meant required mapping the distribution of galaxies across hundreds of millions of light years and calculating the gravitational forces they exert, work that occupied astronomers through the late 20th century and continues today as surveys reach deeper into space. The journey through the cosmic web continues, as it has for billions of years, the local group falling along its filament toward regions of higher density while the universe expands around it. Eventually, billions of years from now, our local neighborhood will have merged into a single massive cluster. The Milky Way and Andromeda combined. The local group absorbed into the structure, flowing toward the Virgo Great Attractor Shapley region, creating one node in the Great Web. But that future remains distant, and for now, the motion continues smoothly, imperceptibly, carrying us through space at speeds that would seem impossible if we could somehow feel them. And all these motions, from the rotation of Earth to the flow through the cosmic web, were gradually discovered by observers who looked carefully at the heavens and noticed patterns that revealed movement where stillness had been assumed. A story of expanding perspective that unfolded across centuries as each generation saw further and understood more deeply. For most of human history, the Earth felt still and the heavens appeared to move, a natural conclusion drawn from direct experience and careful observation of the sky. The ground beneath offered no sensation of motion, no vibration or shift to suggest it traveled through space, while the sun, moon, and stars clearly moved across the sky daily, rising in the east and setting in the west with perfect regularity. This apparent motion led naturally to models where Earth remained stationary at the center of the cosmos, while everything else rotated around it. Wheels within wheels, carrying the celestial objects through their complex paths. The ancient Greeks developed sophisticated geocentric models that could predict planetary positions with reasonable accuracy, though the predictions required complicated arrangements of circles called epicycles. Ptolemy's model from the 2nd century codified this approach, placing Earth at the center with the moon, sun, and planets orbiting on circular paths that themselves moved on other circular paths, creating loops and reversals in the planetary motions as seen from Earth. The model worked well enough for navigation and calendar keeping, and it matched the philosophical view that Earth, as the central and most important place in creation, should naturally sit still while everything else moved. Challenges to this view emerged slowly, driven by careful observations that revealed problems with the geocentric model's predictions. In the early 1500s, Nicolaus Copernicus proposed a heliocentric model, placing the Sun at the center, with Earth and the other planets orbiting around it. A radical suggestion that overturned the philosophical assumptions of the time. The model simplified the explanation of planetary motions, eliminating most of the epicycles by recognizing that retrograde motion, the apparent backward movement of planets against the background stars, resulted from Earth overtaking outer planets or being overtaken by inner planets as both moved on their respective orbits. Copernicus's model faced significant resistance, both because it contradicted direct experience, which seemed to show Earth sitting still, and because it challenged theological views about Earth's central importance. But the model made predictions that could be tested through observation, and as astronomical instruments improved, evidence accumulated supporting the heliocentric view. Galileo Galilei's telescopic observations in the early 1600s provided crucial support, particularly his discovery of moons orbiting Jupiter, which demonstrated that not everything circled Earth, and his observation of Venus's phases, which matched the predictions of the Copernican model, but not the Ptolemaic one. Proving that Earth actually rotated required detecting physical evidence of the rotation, not just astronomical observations that the heliocentric model explained better. In 1649, Giovanni Battista Riccioli attempted to use a falling object to detect Earth's rotation, reasoning that if Earth turned eastward while an object fell, the object should land slightly west of the drop point. The effect proved too small to measure reliably with the equipment available, and the experiment failed to demonstrate rotation conclusively. The proof came much later, in 1851, when French physicist Léon Foucault suspended a heavy pendulum from the dome of the Pantheon in Paris and demonstrated that the plane of its swing rotated slowly over the course of hours. The pendulum itself maintained a constant plane of oscillation relative to the fixed stars, as the laws of physics required, but the floor beneath it rotated as Earth turned, creating the illusion that the pendulum's swing rotated clockwise over time. At the Pantheon's latitude of about 49 degrees north, the rotation took approximately 32 hours to complete one full circle, the rate depending on latitude, according to a simple trigonometric relationship. This elegant demonstration provided direct, visible proof that Earth rotated, something anyone could watch happening over the course of a day. Proving Earth's orbital motion around the Sun proved even more challenging, because the scale of the solar system made the effects subtle and difficult to measure. If Earth truly moved around the Sun, then the nearest stars should show apparent shifts in position when viewed from opposite sides of Earth's orbit, an effect called stellar parallax. The absence of observable parallax had been used for centuries as an argument against Earth's motion, with critics noting that if Earth moved 93 million miles from one side of its orbit to the other, surely nearby stars would appear to shift position against more distant background stars. The problem was not that parallax failed to occur, but that even the nearest stars sit so far away that their parallax angles remain extremely small, far smaller than the resolution of telescopes available before the 19th century. In 1838, German astronomer Friedrich Wilhelm Bessel finally succeeded in measuring the parallax of the star 61 Cygni, detecting an annual shift of about 0.3 seconds of arc, an angle equivalent to viewing a coin from about 10 miles away. This measurement proved Earth orbited the Sun, and also provided the first direct measurement of the distance to a star. establishing the scale of interstellar space for the first time. Understanding the sun's motion through the galaxy required first understanding that the Milky Way was a galaxy at all, and that the sun occupied a position within it, rather than sitting at the center of the universe. William Herschel, in the late 1700s, mapped the distribution of stars visible through his telescopes and recognized that they formed a flattened disk, suggesting the sun sat within a large stellar system. He also analyzed the proper motions of bright stars and detected a systematic pattern, suggesting the sun moved toward a point in the constellation Hercules, identifying the solar apex we discussed earlier. Though he did not yet understand this motion as part of a galactic orbit, the galactic rotation itself became clear only in the early 20th century, when Harlow Shapley mapped the distribution of globular clusters and realized the sun sat far from the center of their distribution, placing us in the outer regions of the galaxy rather than at its center. Jan Oort, in the 1920s and 30s, studied the motions of stars at different distances from the galactic center and detected the differential rotation pattern, measuring how orbital speeds varied with radius and revealing that the galaxy rotated as a whole, though not as a solid body. This work laid the foundation for using rotation curves to probe the mass distribution in galaxies. Research that would later reveal dark matter when the curves failed to match the visible matter's predictions. The motion relative to the cosmic microwave background was discovered in the 1970s and refined through the 1990s and early 2000s as satellites measured the microwave sky with increasing precision. The Cosmic Background Explorer, COBE, launched in 1989, detected a dipole pattern in the cosmic microwave background temperature, with one hemisphere of the sky appearing slightly warmer and the opposite hemisphere slightly cooler than the average temperature. This dipole indicated motion toward the warmer hemisphere at about 370 kilometers per second, representing the local group's velocity relative to the cosmic rest frame defined by the ancient radiation filling space. Later missions, including the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, refined these measurements, determining our motion through the CMB with extraordinary precision and creating detailed maps showing the dipole pattern along with the tiny temperature fluctuations that represent the seeds of cosmic structure. The direction of motion pointed toward the constellation Leo, though the motion results from the combination of the Milky Way's motion through the local group and the local group's motion through the larger cosmic web, a complex sum of multiple velocity components. Each discovery expanded humanity's perspective, revealing that what appeared still actually moved, and that motions occurred on scales almost impossible to comprehend directly. The progression from believing Earth sat motionless to understanding we travel through space at over 1 million miles per hour took centuries of careful observation, theoretical development, and technological innovation. Each step required overcoming the intuitive sense that motion should be felt, accepting instead that constant velocity produces no sensation, regardless of speed, and trusting that indirect evidence from changing stellar positions and Doppler shifts revealed real motions even when our bodies registered nothing. The psychological shift from stillness to motion represented a profound change in human self-understanding, part of the broader Copernican revolution that displaced Earth and humanity from the center of creation to a modest position in the cosmic suburbs. Yet the motions discovered were not random but followed patterns, obeying physical laws that operated universally, creating a cosmos where motion itself became understandable even as it expanded to scales that dwarfed the Earth and everything on it. And with all these motions mapped and measured, a question naturally arises about what motion even means and whether any reference point can be called truly at rest. Motion exists only in relation to something else, a fundamental principle that emerges from the laws of physics as developed over centuries of investigation. We can measure Earth's rotation relative to the distant stars, its orbital speed relative to the Sun's orbital velocity relative to the galactic center, but each of these measurements depends on choosing a reference point and calculating motion with respect to that point. No experiment performed within a closed laboratory, moving at constant velocity, can determine whether the laboratory moves or sits still. Because the laws of physics operate identically in all reference frames that move uniformly, a principle called Galilean relativity, later refined and extended by Einstein into special and general relativity. This relativity of motion means that asking whether something moves in an absolute sense has no answer within classical physics. We can only ask whether something moves relative to something else, choosing our reference frame based on convenience or interest. Earth rotates relative to the distant stars, a useful reference that defines the sidereal day and allows accurate timekeeping. Earth orbits relative to the Sun, the obvious central mass dominating the solar system's gravitational field. The Sun orbits relative to the galactic center, the point around which the galaxy's structure organizes itself. Each reference frame serves a purpose, but none holds special claim to being the absolute standard against which all motion should be measured. However, the universe itself provides a unique reference frame through the cosmic microwave background radiation. Ancient light released about 380,000 years after the Big Bang, when the universe cooled enough for neutral hydrogen to form and photons to travel freely through space. This radiation fills the universe uniformly in all directions, arriving at Earth from every point in the sky with remarkable uniformity, showing the same temperature of about 2.7 Kelvin everywhere, after accounting for one systematic difference. That difference takes the form of a dipole pattern, one hemisphere of the sky showing radiation slightly blue-shifted and therefore appearing slightly warmer, while the opposite hemisphere shows radiation slightly red-shifted and appearing slightly cooler. The dipole arises from our motion through the cosmic microwave background, the Doppler effect shifting the radiation's frequency up in the direction we move toward and down in the direction we move away from. Measuring the magnitude of this dipole reveals our speed relative to the cosmic microwave background, about 370 kilometers per second. And the direction of the warmer hemisphere shows which way we move, toward the constellation Leo. This motion includes all the components we have discussed: Earth's orbit, the Sun's orbit around the galaxy, the Milky Way's motion through the local group, and the local group's motion through the cosmic web, all combined into one net velocity relative to the most distant observable reference. The cosmic microwave background provides something close to a universal rest frame, a reference point that exists everywhere in space, and that defines a frame in which the ancient radiation appears isotropic, the same in all directions. An observer moving relative to the CMB sees the dipole pattern, while an observer at rest, relative to the CMB, would see perfectly uniform temperature in all directions. No preferred direction of motion imprinted on the radiation. This frame has special significance because it represents the frame in which the universe appears most symmetric, where the expansion of space proceeds uniformly in all directions without any bulk motion superimposed. The cosmic rest frame, defined by the CMB, allows astronomers to separate our local motions from the overall expansion of the universe. Distant galaxies recede from us because the space between us expands, carrying galaxies apart at speeds proportional to distance, a relationship discovered by Edwin Hubble in the 1920s. But each galaxy also has its own peculiar velocity, motion through space relative to the local cosmic rest frame, caused by gravitational attraction from nearby structures. The motion we measure toward the great attractor represents our peculiar velocity, our deviation from pure expansion, and this motion shows up as the dipole in the cosmic microwave background. The existence of this cosmic rest frame does not violate relativity, because the frame is defined by the matter and radiation content of the universe, not imposed from outside. The laws of physics still operate identically in all uniformly moving reference frames, but the cosmic microwave background provides a detectable standard that allows observers anywhere to determine their motion relative to the universe's large-scale structure. Two observers in distant galaxies could both measure their motion relative to the CMB and thereby calculate their relative velocity, even if they could never communicate directly or observe each other. From our perspective here on Earth, the cosmic microwave background appears almost uniform except for the dipole from our motion, and tiny fluctuations representing the seeds of structure formation in the early universe. These fluctuations, only about 1 part in 100,000 in amplitude, show slightly warmer and cooler regions that correspond to slightly denser and less dense patches in the early universe. Regions that would eventually grow into galaxy clusters and voids through gravitational collapse. The dipole dominates these fluctuations by far, about 1,000 times larger, and must be subtracted from the data to reveal the underlying pattern of primordial fluctuations. Maps of the cosmic microwave background show the full sky projected onto a flat surface. Much like maps of Earth flatten the globe into 2 dimensions. The dipole appears as a gradient from one side of the map to the other, the Doppler shifted temperature creating a smooth transition from warmer to cooler across the sky. After removing this dipole, the much smaller primordial fluctuations appear as a mottled pattern of warm and cool spots, the famous map of the early universe that shows what the cosmos looked like when it was only 380,000 years old, before the first stars formed or galaxies assembled. Understanding that we move at 370 kilometers per second relative to the cosmic microwave background allows us to correct our observations of distant objects, accounting for our motion when measuring their properties. It also provides context for interpreting the motions we observe, separating local gravitational flows from the overall cosmic expansion, and revealing the large-scale structure responsible for galaxy motions across hundreds of millions of light-years. The frame defined by the CMB represents as close to an absolute reference as the universe provides, a standard that exists naturally from the structure of the cosmos itself. Yet even with this special reference frame, the fundamental principle remains that motion is relational, defined by comparing one thing to another. The CMB provides a particularly useful and physically meaningful reference, but observers could choose other references if desired. A traveler moving at 99% of light speed relative to the CMB would still observe the laws of physics operating exactly as they do for us. Time and space transforming according to relativity to preserve the consistency of physical law, though their view of the universe would appear dramatically distorted by Doppler shifts and relativistic aberration compressing the star field ahead and stretching it behind. The motions we experience, layered one upon another from Earth's spin to the cosmic flows, all proceed without producing any sensation, because we move smoothly without acceleration, carried along by gravity and momentum through a universe that offers no resistance to motion in the near vacuum of space. The stillness we feel reflects the constant velocity of our journey, the absence of forces pushing us this way or that, while the motions themselves reveal themselves only through patient observation of changing positions over time. And these motions have carried us on a journey through the galaxy across billions of years, a path we can trace backward into the deep past and forward into the distant future. The Sun formed about 4.6 billion years ago from the collapse of a cloud of gas and dust in a region of the galaxy far from where we sit today. At that time, the solar nebula condensed somewhere in the disk, perhaps in or near a spiral arm, where molecular clouds concentrate, and star formation proceeds actively, though the exact location remains uncertain. Since formation, the Sun has completed roughly 20 orbits around the galactic center, each orbit taking 230 million years. Each circuit carrying the young solar system through different regions and past different stars, as the journey around the galaxy continued. Rewinding the clock to trace the Sun's path backward through time requires accounting for the complexities of galactic motion, the vertical oscillation through the plane, and the slight wobble in orbital radius, as gravitational perturbations from spiral arms and giant molecular clouds nudge the trajectory. Computer simulations can approximate the path by integrating the equations of motion backward, though uncertainties in the galaxy's past structure and mass distribution limit the precision of such calculations. Still, the broad outlines emerge, showing the Sun moving on an elliptical path around the galactic center, bobbing up and down through the disk, occasionally passing through spiral arms, and more often traversing the quieter inter-arm regions. 230 million years ago, when the Sun last occupied roughly the same position in its orbit as today, Earth was experiencing the early Triassic period. Dinosaurs had just emerged. Mammals existed as small nocturnal creatures, and the supercontinent Pangaea dominated the surface geography. The Sun's neighbors in space differed from the stars we see nearby today, as each star's peculiar motion carried it on its own path over that immense time span, rearranging the local stellar population completely. Stars that were close then have drifted far away, and stars that are close now were distant or had not yet formed. 460 million years ago, 2 orbits back, Earth was in the Ordovician period with no life yet on land, all complex organisms confined to the seas. The Sun occupied a position on the opposite side of its orbit from today, about 52,000 light-years from its current location, measured around the circumference of the orbital path. The view of the galaxy from Earth would have been reversed, with the galactic center appearing in the opposite part of the sky compared to where we see it now. And the Milky Way's band crossing the night sky at different angles as the tilt of Earth's axis relative to the galactic plane shifted over time due to precession and other long-term changes. Going back 1 billion years, roughly 4 orbits ago, Earth was in the Proterozoic eon, with only simple multicellular life just beginning to emerge. The Sun had completed about 16 orbits total by that time, and its path had carried it through at least several and possibly many passes through spiral arms, each encounter potentially disturbing the Oort cloud and sending comet showers toward the inner solar system. Some researchers have proposed connections between spiral arm passages and mass extinctions on Earth, suggesting that increased comet impacts or cosmic ray exposure during arm passages might stress the biosphere, but the evidence remains ambiguous and the timescales uncertain. The last time the solar system crossed a major spiral arm may have occurred tens of millions of years ago, though pinning down the exact timing requires knowing the positions of the arms over time and the Sun's precise path, both of which carry significant uncertainties. The crossing would have taken about 10 million years given the arm's width and our speed, during which time the environment around the solar system showed higher stellar density, more frequent supernovae in the region, and greater concentrations of gas and dust. The effects on Earth remain speculative, possibly including climate changes from variations in cosmic ray flux or increased bombardment from comets. But disentangling these potential signals from Earth's complex geological and biological record proves difficult. Looking forward in time, the Sun will continue its journey around the galaxy, completing its current orbit in about 230 million years, and beginning the 21st circuit. By that time, Earth's continents will have drifted into new configurations, possibly forming a new supercontinent as the Atlantic Ocean closes and the Americas collide with Europe and Africa. Though predicting continental positions that far ahead carries enormous uncertainty. The Sun will likely pass through another major spiral arm at some point in the next few 100 million years, encountering denser regions and a more active stellar environment before emerging into quieter inter-arm space again. The stellar neighborhood will transform completely over such timescales, with current nearby stars moving far away and new stars approaching from regions distant today. Barnard's star, currently 6 light-years away and approaching, will pass by at its closest approach in about 10,000 years at just under 4 light-years distance before receding into the distance. Proxima Centauri will cease to be our nearest neighbor in about 27,000 years, replaced by other stars passing through the region. Over millions of years, the entire population of nearby stars will turn over multiple times, each generation of neighbors replaced by new stars arriving from different parts of the galaxy. The night sky will change dramatically across such deep time, the familiar constellations slowly distorting as each star's proper motion shifts positions relative to the others. The Big Dipper will lose its recognizable shape within about 100,000 years, becoming stretched and deformed as its stars drift apart. 50,000 years from now, Vega will serve as the North Star rather than Polaris, due to the precession of Earth's axis, which causes the North Celestial Pole to trace a circle among the stars over a period of about 26,000 years. But this precession operates on timescales far shorter than the changes from stellar proper motion, which alter the positions of the stars themselves rather than just Earth's orientation. 1 million years from now, assuming Earth still orbits the Sun in a stable configuration, the night sky will show a pattern of stars largely unfamiliar to modern observers. The brightest stars will differ, some currently bright stars having moved far away, while fainter stars currently too distant to see easily will have approached and become prominent. The Milky Way's band will cross the sky in roughly the same way because the galactic plane changes orientation far more slowly than individual star positions. But the detailed structure along that band will show different bright regions and dark nebulae as our position shifts. 100 million years forward brings us to a time when the Sun will have moved about 40% of the way around its current orbit, finding itself in a significantly different region of the galaxy. The Andromeda Galaxy will have approached measurably closer, appearing slightly larger in the night sky, though still far from dominating the view, as it will during the eventual merger, billions of years hence. Earth's surface will have transformed through plate tectonics, mountain ranges rising and eroding, ocean basins opening and closing. The familiar geography of the present, replaced by configurations we can barely guess at with current understanding. The continuity through all this change remains the motion itself, the steady orbit around the galactic center that has continued since the Sun formed and will continue until the galaxy's structure changes fundamentally through mergers or other catastrophic events. The speed of 450,000 miles per hour persists with only minor variations as the Sun follows its path through the galaxy's gravitational field. The journey continuing through time, regardless of what happens on the small rocky planet third from the star, regardless of whether life survives there or consciousness persists to observe the changing heavens. And this ancient journey, this motion through the galaxy that carries us past countless stars and through spiral arms over hundreds of millions of years, combines with all the smaller motions we have explored to create the total movement we experience each moment. A sum of velocities that reaches extraordinary magnitude when measured in the right direction through space. All the motions we have followed come together to create the total velocity we experience through the universe, each layer adding to the previous ones in a complex vector sum that depends on direction and time. At this particular moment, the combination of Earth's rotation, Earth's orbit around the Sun, the Sun's orbit around the galactic center, the Milky Way's motion through the local group, and the local group's motion through the cosmic web creates a net velocity that reaches approximately 1.3 million miles per hour when measured in the direction toward the Great Attractor region. This number represents not the speed in all directions simultaneously, but the maximum speed in one particular direction, where the motions align to produce the greatest combined velocity. The rotational speed at the equator contributes about 1,000 miles per hour eastward, though this motion points in constantly changing directions as Earth spins, sometimes aligning with the orbital motion and sometimes opposing it, depending on time of day. Earth's orbital speed around the Sun adds about 67,000 miles per hour in the direction of our current position along the orbit, changing throughout the year as we move around the ellipse. The Sun's orbital motion around the galactic center contributes 450,000 miles per hour in the direction toward the part of the galaxy we currently approach in our orbit, roughly toward the constellation Cygnus, though the exact direction depends on how we define the reference frame. The Milky Way's motion through the local group toward Andromeda adds about 250,000 miles per hour, and the local group's motion through the cosmic web toward the Great Attractor and beyond adds the largest component, roughly 600,000 miles per hour. Adding these velocities requires accounting for their different directions, using vector addition to combine components pointing in different ways. In the specific direction toward the Great Attractor region, the alignment happens to produce a sum close to 1.3 million miles per hour, a remarkable speed that would cross the distance from Earth to the Moon in about 11 minutes. Yet despite this tremendous velocity, we feel absolutely nothing. No rushing wind, no sense of movement, no indication whatsoever that we travel through space at such extraordinary speed. The reason lies in the fundamental nature of motion in physics, where constant velocity at any speed produces exactly the same experience as complete rest. Our bodies detect acceleration, changes in velocity, whether in magnitude or direction, but uniform motion creates no sensation regardless of how fast we move. An aircraft passenger traveling at 500 miles per hour feels the same stillness as someone sitting in a parked car, noticing motion only when turbulence or turns introduce acceleration that the body can detect. The smoothness of our cosmic journey results from traveling through a near vacuum where nothing resists our motion, and from the gravitational nature of the forces guiding us. Gravity pulls on every part of our bodies equally, creating no differential forces that we could feel as pressure or tension. We fall freely along with Earth around the Sun, and the entire solar system falls freely in its orbit around the galactic center, and the galaxy falls freely through the cosmic web. All these motions proceeding without friction or drag or anything pushing against us. The experience is one of perfect weightlessness along the directions of motion, though Earth's gravity holds us to the surface and creates the sensation of weight we experience daily. The atmosphere travels with us, rotating along with Earth and orbiting along with the planet, and participating in all the larger motions too, so no wind arises from our motion through space. The air molecules share our velocity completely, moving along with the surface beneath them and carrying that motion forward into all the larger scales of movement. The oceans move with us, the clouds move with us. Every bird flying through the sky already shares the velocity of the ground it took off from, and all the cosmic velocities that ground possesses. Nothing in our environment provides a contrasting reference point, no fixed background against which our motion could be perceived, and so the stillness feels absolute and complete. This principle, that uniform motion cannot be distinguished from rest, stands as one of the foundational insights of physics. Formalized by Galileo centuries ago and later incorporated into Einstein's theories of relativity, the laws of physics operate identically in any reference frame moving at constant velocity, meaning experiments conducted on Earth produce the same results they would produce on a spacecraft moving at 1.3 million miles per hour through empty space. No experiment performed entirely within a closed room could reveal whether that room sits still or moves at constant speed, because the two situations are physically equivalent. Only acceleration, only changes in velocity, create effects that can be detected, like the pressure felt when a car speeds up, or the sensation of lightness when an elevator begins descending. Our cosmic journey proceeds without such accelerations in any direction we could perceive. The changes in velocity, occurring so gradually across such enormous timescales, that they remain imperceptible. Earth's rotation maintains nearly constant speed, slowing by mere milliseconds per century, far too gradual for human senses to detect. The orbit around the Sun follows an ellipse with changing speed, faster at perihelion and slower at aphelion. But the acceleration involved amounts to mere fractions of a millimeter per second squared, utterly negligible compared to the sensations we experience in daily life. The Sun's orbit around the galactic center changes direction constantly, creating centripetal acceleration toward the galactic core. But spread across such immense distance and orbital period that the acceleration becomes vanishingly small. The perspective from within our reference frame shows a universe at rest relative to us, with the Sun fixed in its position in the sky throughout each day until Earth's rotation carries it westward. The stars hold their places in familiar constellations night after night, year after year, their proper motions too slow for the unaided eye to perceive across human lifetimes. The moon rises and sets. The planets wander against the background stars, but all these motions appear as movements of those objects through a stable sky, not as evidence of our own tremendous velocity through space. From inside the reference frame, we occupy the center of observation, and everything else moves while we remain still. Yet shift the perspective outward, step back to view the solar system from beyond, and the picture transforms completely into one of constant motion and flow. Earth becomes a blue sphere spinning steadily, completing rotations every 24 hours, with clouds swirling across its surface and the Terminator line sweeping westward across continents and oceans. The planet traces its elliptical path around the Sun, moving visibly across its orbital plane, when time accelerates to show years passing in seconds. The Sun and its family of planets glide together through the local stellar neighborhood, passing other stars that drift on their own paths through the galaxy's structure. Pull back further still, and the Milky Way reveals itself as a great spiral, slowly rotating, with our Sun appearing as one unremarkable point of light, 2/3 of the way from center to edge. Watch across millions of years, and the Sun's position shifts, moving through its orbital path, passing through regions of higher and lower stellar density, as it weaves slightly above and below the galactic plane. The galaxy itself moves through the local group, approaching Andromeda with patient inevitability, the distance between them shrinking by about 250,000 miles each hour, though billions of years remain before any close encounter occurs. From the cosmic scale, the local group appears as one small concentration of galaxies flowing along the filaments of the cosmic web toward denser regions beyond, participating in the great currents that move clusters and superclusters across hundreds of millions of light years. The perspective reveals motion everywhere, galaxies streaming through space, their light shifted toward red or blue, depending on whether they recede or approach, the expansion of space itself carrying distant structures away, while gravity pulls nearby structures together. In this view, stillness nowhere exists. Everything flows and moves and journeys through the evolving universe. The paradox emerges most clearly in the contrast between these perspectives. The absolute stillness we experience and the extraordinary motion we actually undergo, creating a gap that challenges intuition. Standing on solid ground beneath a quiet sky, feeling no wind, sensing no movement, the mind naturally concludes that here stillness reigns, that this moment unfolds in a place at rest. Yet the reality involves speeds that would cross continents in minutes and span the solar system in hours, velocities that seem to belong to science fiction rather than to the everyday experience of drinking tea or watching stars appear as twilight fades. The resolution of this paradox lies in understanding that both perspectives tell truth, that stillness and motion coexist, depending on the frame of reference chosen for measurement. Relative to the ground beneath our feet, we truly do remain motionless when we stand in one place, moving only when we walk or drive or fly. Relative to the Sun, we orbit at tremendous speed, covering nearly 2 million miles each day along Earth's path. Relative to the galactic center, we race through space at 500,000 miles per hour. And relative to the cosmic microwave background, we move at speeds that reach beyond 1 million miles per hour in certain directions. None of these descriptions contradicts the others, each one measuring velocity against a different reference point and finding a different answer. The question is not which measurement is correct, but rather which reference frame serves the purpose at hand. For daily life, the ground provides the natural reference. For understanding seasons and solar energy, the sun provides context. For galactic astronomy, the galactic center, or the local standard of rest, becomes relevant. And for cosmology, the cosmic microwave background offers the nearest thing to a universal reference frame. Motion reveals itself as fundamentally relative, always measured against something, never absolute or independent. This relativity of motion extends throughout the universe, affecting every object and structure across all scales of distance and time. The star Proxima Centauri moves relative to us at about 25 miles per second, approaching slowly, while Barnard's star approaches faster at about 87 miles per second. And both stars move relative to the galactic center at hundreds of miles per second. The Andromeda galaxy approaches us at about 250,000 miles per hour. But an observer in Andromeda would measure us approaching them at the same speed, each reference frame equally valid. The cosmic web flows and shifts, galaxies moving along filaments and falling toward attractors, and all these motions unfold simultaneously. Every object moving relative to every other object in ways that depend on position and velocity and the gravitational influences shaping trajectories. These motions have continued for billions of years, persisting since the structures formed that now populate the universe. The galaxy's rotation began when the cloud of gas that would become the Milky Way started collapsing under its own gravity. Conservation of angular momentum, transforming slow initial rotation into the faster spin of the condensed structure. The sun's orbit around the galactic center began when the solar nebula collapsed to form our star, inheriting the angular momentum of the particular region of the galaxy where it formed. And that orbit has continued for 4.6 billion years, completing roughly 20 circuits around the galactic center since the sun ignited. Earth's rotation began during the planet's formation, when countless collisions between planetesimals imparted angular momentum that summed to create the spin we experience today. The great impact that formed the moon altered Earth's rotation, likely shortening the day and tilting the axis. But the fundamental rotation has persisted since those early violent times, gradually slowing under the moon's tidal influence, but never ceasing. The orbit around the sun began when Earth's mass accumulated from the swirling disk of material surrounding the young star, gravity and angular momentum balancing to create the stable ellipse that has carried Earth through more than 4 billion circuits, each one bringing another year of seasons and change. The motions will continue far into the future, persisting as long as the structures themselves endure. Earth will keep rotating for billions of years to come, though the days will lengthen slightly as the moon continues to recede and tidal forces gradually slow the spin. The orbit around the sun will persist until the sun exhausts its hydrogen fuel and begins to expand into a red giant, swelling to perhaps engulf Mercury and Venus and altering the conditions throughout the inner solar system. The sun's orbit around the galactic center will continue for billions of years, completing many more circuits, though perturbations from passing stars and molecular clouds will slightly alter the path over time. The Milky Way and Andromeda will approach each other across the next 4 billion years, their mutual gravity pulling them together until their first close passage occurs, followed by a long gravitational dance that will eventually merge them into a single larger galaxy. The merged structure will continue moving through the local group and participating in the cosmic flows that pull galaxies toward denser regions. Even the expansion of space will continue, carrying distant structures beyond the cosmic horizon, while gravitationally bound systems like galaxy clusters maintain their integrity against the general expansion, creating islands of persistent structure in an expanding cosmos. Through all these changes, the fundamental nature of motion will remain unchanged. Objects moving relative to other objects, reference frames defining what counts as stillness and what counts as speed. Future astronomers observing from worlds circling distant stars will measure their own complex velocities through nested motions, finding themselves in motion around their stars, around galactic centers, through cosmic structures, all while feeling the same stillness we feel now. The principle holds universally, the equivalence of constant motion and rest, creating a cosmos where every observer can equally claim to be at rest while others move, or to be in motion while using different references. What we participate in, then, is something both extraordinary and ordinary, remarkable in its scale and speed, yet utterly natural in its effects and persistence. The 1.3 million miles per hour represents a kind of cosmic achievement, a sum of all the scales of motion from planetary rotation through cosmic flows. Yet it produces no sensation, no experience, no indication beyond the mathematical calculation that adds vectors and finds velocities. We remain passengers on a planet that spins and orbits, riding a star that circles a galaxy, traveling with that galaxy through the universe, and all of it happens in perfect silence and perfect smoothness. The vacuum of space providing no resistance, and gravity providing the gentle, constant pull that curves trajectories into orbits and flows. The journey continues beneath the night sky. The same stars, visible overhead, that guided ancient travelers, now revealing themselves through modern astronomy to be fellow travelers themselves, all moving through the galaxy's slow rotation. The constellations we recognize will slowly distort across thousands of years as stars move relative to each other, their individual motions eventually breaking apart the familiar patterns our ancestors named and told stories about. Orion's belt will separate, the Big Dipper will change shape, the bright stars of summer will drift to new positions, and new configurations will emerge, all from the same stellar motions that carry us through space alongside our neighboring stars. Somewhere in the distant future, humans or their descendants might look up at a sky transformed by millions of years of stellar drift, seeing patterns we would not recognize. And they too will participate in the same motions, riding Earth through its orbit, carried by the Sun around the galactic center, moving through cosmic structures we are only beginning to map. They will measure their velocities and find similar numbers, motion persisting across deep time, the dance continuing as it has always continued. The 1.3 million miles per hour might change slightly as the Sun's position in its orbit shifts, as the local group's motion through the cosmic web responds to evolving gravitational influences, but motion itself will remain. And here, now, in this particular moment along that journey, we rest beneath the sky, participating in all those motions without feeling any of them. The stillness complete and the motion equally real. The bedroom window frames stars whose light left their surfaces years or centuries ago, traveling through space to arrive at this moment, and in the time it took that light to cross the distance. We moved through space ourselves, Earth circling the Sun multiple times, the Sun moving along its galactic orbit, the galaxy itself shifting position in the cosmic web. The light found us anyway, arriving at eyes that traveled to meet it, the intersection of photon paths and planetary trajectories, creating the simple experience of seeing a star on a quiet night. The totality of our motion through the universe resolves into something almost poetic in its character. Vast speeds producing perfect stillness, tremendous journeys unfolding, while we sleep and wake and go about our days. The cosmos carrying us forward through time and space without asking anything of us in return. We need do nothing to participate. No effort required to maintain the rotation or the orbit, or the galactic circuit, or the cosmic flow. The motions simply continue. Ancient rhythms established billions of years ago, physical laws ensuring their persistence. And we ride along, awake or asleep, aware or unaware. Passengers on a planet traveling through the universe at 1.3 million miles per hour in a particular direction at a particular moment, while simultaneously resting perfectly still relative to the ground beneath us and the air around us and the familiar objects that fill our immediate world. The journey has no destination, no final point where motion ceases and arrival occurs, only the ongoing travel itself, the continuous process of moving through space and time that defines existence in this universe. We journey together, every human sharing these velocities, every plant and animal and mountain and ocean moving together through the cosmos. And beyond Earth, every planet and moon and asteroid shares the solar system's motions. And beyond the solar system, every star in the galaxy participates in the galactic rotation. And beyond our galaxy, every structure moves through the cosmic web according to the gravitational influences that shape the largest scales of the universe. All of it in motion, all of it proceeding, the great cosmic current flowing onward through time.